So our second speaker this section is Mark Werder from McGill University.
Okay, so thanks for having us at the conference. The topic of the talk is classical communication over networked quantum channels. Okay. And when you're looking at this title, you may be wondering, why is this guy up here talking about classical communication at the Quantum Information Processing Conference? Well, there are two answers to this question. The first of which, from an engineering perspective, this is a setting in which we know that we can obtain something we might call a quantum supremacy, in the sense that a quantum strategy can outperform a classical one. In this setting, the classical strategy is for the receiver to perform individual measurements of the channel outputs, and the quantum strategy is for the receiver to perform a collective measurement of the channel outputs. This quantum supremacy is particularly pronounced for optical channels in the low photon number regime. The second answer is sort of from a pioneering perspective. We wanted to push farther into this domain of quantum network information theory. There were a few papers out there on this topic, and many of them could just exploit the coding theorem of Halevo, Schumacher, and Westmoreland. But when we pushed farther into this domain, we found that we couldn't use these tools. We would have to develop new tools and techniques, and so that's what we did. And as a result, these two papers right here came out of this work, and they sort of started uncontrollably producing offspring in the form of these papers. So to get on with the talk, the setting we considered is the interference channel. This is something that's known in the classical literature. And we considered a quantum interference channel. It's a channel with two senders and two receivers. And we simplified the model somewhat by considering channels with classical inputs and quantum outputs. It turns out this model is rich enough to capture the difficulty of the problem. And if you come up with strategies for this channel, it can apply to a channel with quantum inputs and quantum outputs. Okay, so the idea is that sender 1 has access to this classical 1 input port, and sender 2 has access to this classical X2 input port. And conditional on these inputs, a density operator, the channel prepares it on the tensor product Hilbert space of the two receivers, B1 and B2, I guess Bob 1 and Bob 2. And so the information processing task corresponding to the setting is that sender 1 prepares, it wants to transmit some message over the channel and encodes this message into a form that can be input into many uses of the channel, this interference channel. Sender 2 likewise prepares some message M2 that she then encodes into a classical input, a classical code word that can be input into many uses of the channel. The channel then prepares some output for the receiver, and the first receiver performs a collective measurement to figure out the message that sender 1 was transmitting, and receiver 2 likewise performs a collective measurement to figure out the message that receiver 2 is transmitting. And the unique thing about this channel is that the first sender is only interested in communicating with the first receiver, and the second sender is only interested in communicating with the second receiver. So there can be interference along the way as this transmission takes place. Now, what we found when we were looking at the literature, in the classical information theory literature, is that it was important to consider the effective multiple access channels that this interference channel induces. Okay, so a multiple access channel is one with two senders and one receiver. Okay, so if I just trace over the second receiver, then the effective multiple access channel is given by this going to the first receiver. And similarly, there's an effective multiple access channel going to the second receiver, okay, found by tracing over the first receiver. And so coding strategies for the multiple access channel can be used to make coding strategies for the interference channel, okay? And so for the remainder of the talk, I'm going to be focusing on the multiple access channel. And if you have further questions, we can talk about that later. So the multiple access channel, the diagram is similar. We have two senders interested in communicating their independent messages to one receiver, and the receiver performs a collective measurement to figure out these messages that the senders transmitted. So this channel, we're also considering a CCQ channel with 2 classical inputs and 1 quantum output. And what Andreas Winter found some time ago as a graduate student is that this rate region over here is achievable for communication over this channel. Okay, and so R1 is the rate at which sender 1 can communicate to the receiver, and R2 is the rate at which sender 2 can communicate to the receiver. And these information quantities are mutual informations that determine the correlations that can be established with the senders and the receiver. Okay? And these information quantities are evaluated with respect to a classical quantum state of this form. The output of the channel is embedded in this system, and these are classical registers that correspond to the classical systems and these information quantities. These distributions are used by the senders to pick random code books independently. So that's why this distribution has this independent form. And what's unique about this paper, if you look at it, is that Andreas was very excited about using strange fonts in LaTeX. That was sort of the unique feature that I found. Okay, so just to give you a picture of that rate region, this is the rate region we had in the previous slide. It's in the form of a pentagon. What you can show, since x1 and x2 are independent, this information quantity is equal to this one on the top right, and likewise for these information quantities. You can show that via the chain rule for mutual information. Okay? And there are 2 strategies that can be used for coding over a quantum multiple access channel. One is that Andreas used some time back that we call quantum successive decoding. And here is where you can pretty much use the HSW coding theorem, the Halevo-Schumacher-Westmoreland coding theorem, to establish codes for the multiple access channel. And I'll be talking about that a little bit because we had some advances in that direction for a different type of measurement. But what's really needed for the quantum interference channel is a technique called quantum simultaneous decoding. So this is where we need to develop new tools and techniques. And I'll be talking about that as well. Okay, so quantum successive decoding, the idea is for the receiver, for the senders and receiver, just to achieve the corner points of the region. Okay? And they can form a code to achieve this corner point and a code to achieve this corner point. And if they have these codes, they can use one code for a fraction of the channel uses and use the other code for the other fraction of the channel uses. And by varying the fraction with which you use these codes, you can achieve all the points along this sum rate bound, the 45-degree line. Okay, and also, if you have a code that can achieve this rate pair, sender 1 can slightly lower, can keep lowering the rate, and if you examine the proof, you can show that all these points are still achievable with this, by achieving this corner point. Okay, and a similar comment applies to this corner point and all the rates below it. So by time sharing and sort of resource wasting, you can achieve this whole pentagon. Okay, so in a little more detail, sender 1 would decode the receiver would decode sender 1 at a rate equal to this information quantity, which sort of looks similar to what comes up in the HSW coding theorem. Then x1 is available as side information for the receiver to help decode the second sender's transmission. And so by doing this strategy, you achieve this corner point. By a symmetric strategy, you can achieve the other corner point. And so the result, the idea is just use point-to-point communication for the successive decoding strategy. Okay, so just a brief review of how this works. We're sort of getting simpler and simpler as we go along. But we have one sender, one receiver for successive decoding. There's a classical input, a quantum output that is prepared by the channel conditionally on that classical input. And the sender can use some distribution at the input to create code words randomly. And so this creates some code book that corresponds to each message that the sender would like to transmit. And what's also important for the error analysis is to consider the average density operator that the receiver has if he doesn't know the particular letter that's being transmitted. Okay, so this density operator is important as well. This all sounds very similar to what Shannon did about 60 years ago, but the difficulty in the quantum case is designing a decoding POVM. Okay, so this is what Halevo, Schumacher, and Westmoreland did some time back. But what Pranav Sen did in a recent paper was a sequential decoding technique. Okay, so this is very similar, if you look in some classical information theory book, how the decoder would work. There's some received sequence, if it's a classical channel, at the output, and there's a code book, and the receiver just scans through all the code words, determine if the received sequence is jointly typical with one of the code words. Okay, so the idea here in sequential decoding is very similar. This was recently pursued by Seth Lloyd, McCone, and Giovanetti, but Pranab had a better, a simpler error analysis to prove this result. So to describe this, remember this average density operator. You can perform a spectral decomposition of this density operator, and then corresponding to many copies of this density operator, there is a typical projector. Okay, and so this projector projects onto a high probability subspace of all of Hilbert space. But what's nice is that the subspace is exponentially smaller than all of Hilbert space. So it's just tracking where all of the probability is concentrated in Hilbert space. Okay, and corresponding to these particular states, rho xn, which correspond to the classical code words that are transmitted through the channel, there are also conditionally typical projectors which are defined similarly and have similar properties. But the space onto which this projector projects is generally smaller than the space onto which this projector projects. Okay, and so the idea that Halevo, Schumacher, and Westmoreland had was to use these projectors to make a square root measurement, and this is fairly well known. But the sequential decoding idea is just to use these conditionally typical projectors to ask sequentially, in analogy with the classical idea, is it the first code word, is it the second code word, etc., until you get a hit from the measurement. Okay? So the error analysis, the way it proceeds, is if the mth code word is transmitted, that's this rho m state here, you're asking, is it the first code word, is it the second code word? So a correct sequence of events would be that you get no, 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 and then at the mth code word you get a hit, right? And so that, this expression here, the trace under these terms, corresponds to a correct sequence of events, right? So no, 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 yes. And so 1 minus that is the error probability for this sequence of events. Okay, so what Pranab came up with was this non-commutative union bound, which is very much an analogy to the union bound from probability theory. So it could have many applications in other areas of quantum information processing. But generally, this is the general statement of the bound. So if there are a sequence of projectors that sort of correspond to a correct sequence of events, 1 minus that is the complement of those events. And you can upper bound this by the complement of the individual events, just like the classical union bound. Except if these projectors are non-commuting, you need a factor 2 root epsilon, so or 2 in the square root. The square root usually doesn't matter in the error analysis from concavity of the square root. Okay, but applying this bound to this first error probability term up here, you can show that the error will decompose into 2 types of errors. The first is that the transmitted code word is not typical with this projector, and from the fact that the typical subspace is a high probability subspace, we can upper bound this term by epsilon. And there's a technicality where you do need to slip in these average projectors before doing something. I'm sort of sweeping that under the rug here, but it is important. So this is the other type of error, that some other code word gives a hit, okay, besides the one that you actually transmitted. Okay, and so this one, using averaging over the choice of a random code and using this average typical projector to bound eigenvalues of this density operator, this is very important when we generalize for the multiple access channel. Using those 2 things, you can upper bound this type of error by this term. And so this is an exponentially decreasing term in the rate, in the mutual information, times the size of the message set. So if the rate of the message set is just below this rate here, then you can make this exponentially decrease in the limit of many channel uses. Okay, so that's the sequential decoding idea. Back to successive decoding for the multiple access channel, we're going back. To give you a picture of how this works, we can think about effective point-to-point channels that are induced for the multiple access channel. Okay, so sender 1 and the receiver agree for the first part of the decoder that they'll just consider the second sender's input to be noise. Okay, so the noise that they're trying to code against is the noise from the second sender and the noise from the channel. And then they can make a point-to-point code to decode X1 using either the square root measurement of HSW or the sequential decoding technique. And after the receiver has recovered the X1 input, this is now available as side information at the output. And so that this isn't really noise anymore for the second sender. It's now available to the receiver. And so the sender 2 and the receiver agree on a point-to-point code which codes for this channel. Okay? And so what's important here, there's a measurement here, there's a measurement here as well. We'd like to show that the measurement here doesn't disturb the state very much. This is why Andreas introduced this gentle measurement lemma to show that a measurement that succeeds with high probability won't disturb the state very much. Right, and so this second part of the code you can decode at this rate. So this is successive decoding, and you can use square root measurement or sequential decoding. Now on to the main, the part that sort of posed the most difficulty for this project was the quantum simultaneous decoder. Okay, so to give you an idea of how this works, we don't want to achieve just the corner points of the region. We'd like to say as long as the rate pair is along the boundary or inside of this region, we'd like to have a single measurement that can extract both messages at the same time. So sort of a single POVM that can do that. And so that's the idea of the simultaneous decoder, that as long as your rate pairs are along the boundary inside, that you can decode. Okay? And so what we did in these papers, in this work we used the square root measurement designed in a particular way, and Pranav also used the sequential decoder to have the simultaneous decoding approach. Okay, so what we found also is that this simultaneous decoder not only has applications for the quantum interference channel, but also for relay channels and broadcast channels, so we've been looking into this recently. So in constructing a quantum simultaneous decoder, we're going to have several states that we have to consider. Okay, so the first state is, remember we're considering the multiple access channel, 2 classical inputs, 1 quantum output. So the first type of state is where you know both X1 and X2, okay? Then another type of state that we have to consider is where you know X1, but you don't know X2, so you have to average over it. And similarly, there's a state where you know X2, but you don't know X1. And finally, there's the state where you average over both. So all these states are relevant because in the decoder, we're going to have typical projectors that correspond to each of them. Okay, so for this first state, for a tensor product of this state, we're going to have a conditionally typical projector. And for the next type of state, we're also going to have a conditionally typical projector. Same for the next type of state, and then the same for the average state. And what makes this problem seemingly difficult is that these states don't have to commute. And as a result, since these typical projectors are built from the eigenvectors of these states, these don't have to commute. Okay? And we know that we're going to need these in the decoding POVM to bound certain eigenvalues that are there in the error analysis in order to have the correct rates come out. Okay? And so we'll have to impose some ordering of these projectors in the decoding measurement. We know in quantum mechanics, usually the order of operators is very important. Okay, so wait, we said this. So in the sequential decoding approach, we said, or in either approach, we'll need these typical projectors there somehow in the decoding POVM in order to get bounds on eigenvalues. And a particularly clever choice to order these projectors is to have the typical projector that projects onto the smallest space on the inside, followed by one that projects onto a larger space, and followed by one that projects onto the largest space. Okay? This is a positive operator, so you could construct a square root measurement from it, but we'd like to talk about the sequential decoding approach. The problem with this, for the sequential decoding approach, this is a positive operator, but it's not necessarily a projector, right? And the non-commutative union bound that we talked about requires projectors. So we'll have to construct a sort of intersection projector from these operators. And so this was a technical accomplishment in this paper. So just to give you an intuitive idea of how this works, I'm going to give you this picture for the smallest space, and you imagine that this projector projects onto this space, and the slightly larger space is given by this picture, and the largest space is given by this picture. And we can imagine considering vectors in a subspace of the space that this projector projects onto, and considering the vectors, when we project into this space, their length is approximately preserved. Okay, so you're seeing the length is approximately preserved, right? And under this projector, also we'd like the length to be approximately preserved. And so more formally, we can define a projector that I'll call pi prime by taking some orthonormal basis for the space that this projector projects onto, and considering how these vectors, how their length is preserved under these projections, and we'd like the length to be approximately preserved, and furthermore, the resulting vectors should be orthonormal. And so this will constitute some subspace in the pullback on this space. And so this is this subspace where the lengths are approximately preserved. And what follows sort of immediately, this projector has to be less than this one with respect to an operator inequality, because it's the projector, the space that it projects onto is simply smaller than the space that this projects onto. And also, from the length preserving property and the fact that this original subspace was a typical subspace, the shadow of this state in this subspace will be very large. And so then finally we can reach a notion of an intersection projector by taking all the vectors in this space and then mapping them through via these projectors. And so the resulting subspace, there'll be a projector that projects on that, and that is the intersection projector. Notice that, I mean, we had to maintain the order. We had to find a very specific order in which this was done, and that's because these projectors don't commute. Okay? And so important properties that are needed is that sort of by construction, this intersection projector will be less than the desired positive operator we talked about at the beginning. And there's sort of an approximate 1 minus epsilon factor here that I'm not showing. And also, from the fact that this mapping was approximately length preserving, we'll have this high probability property for this projector. Okay, so the decoder, the sequential decoder that acts as this simultaneous decoder, is you're using these intersection projectors to ask. The senders are transmitting a message pair, right? So they may transmit L and M, and you're asking, is it the first message pair? Is it, say, 1, 1? Is it the second message pair, 1, 2? Is it the third message pair, 1, 3? And you scroll through the whole code book until you get a hit. And the simultaneous aspect of this decoding POVM is that you're asking about pairs and not individual messages. Okay? So similar to what we had before, the error when you're doing this, so we'll talk about, the senders transmitted the message pair L and M, so you're asking sequentially, and you want a sequence of no's until you get a hit for the LM projector. So 1 minus that will be the error probability. And using, okay, there's another crucial trick so this is a bit subtle. In constructing this intersection projector, we only used 3 of the 4 typical projectors that were there. We used pi x1, x2, pi x1, and pi. There was another one hanging around that we'd like to use as well. And so the idea there is to effectively change the channel with this other projector, pi x2. Okay, so you smooth the channel a bit, and it doesn't change the channel very much because of the properties of typicality. So that sort of slips in that last projector. Okay, and then you again apply this non-commutative union bound, and the error analysis will have 4 terms instead of the 2 that we saw before, because we have message pairs and we have to consider this different error analysis. So the first type of error, again, is if you're not typical. And from properties of typicality and some extra tricks, we can bound this by some small number using the properties of typicality and this intersection projector construction. And then there will be 3 other terms which correspond to the different boundaries on the rate region. Okay? So the first term in these 3 other terms is the probability that the first message was wrong, but the second message was correct. Okay, and so using this very particular construction and an error analysis, we can upper bound this by this. So this is the size of the first sender's message set, and this is the information quantity corresponding to that bound for the rate of sender 1. And a symmetric type of error is the probability that the second message is wrong, but the first message was decoded correctly. And finally, the probability that both messages are wrong. And so all of these we can upper bound by the terms that appear on the boundary of the rate region. Okay, so, right, so we can use this sequential decoding approach, or we can use similar ideas to make a particular square root measurement to do and at the end, the error analysis will look very similar, but the first part of the error analysis is different in these 2 different approaches. So to conclude, the most important problem going forward is to find a general quantum simultaneous decoder for 3 senders. The construction that we have here, it only works for 2 senders, okay? And it has to do with the way this measurement was constructed in the particular order of operators. And when you go to 3 senders, you'll have 7 error terms and 8 projectors. And so we simply can't handle all of them with the techniques that we were using here. Okay, so this is a very important question, because more broadly, the goal would be to push even further with network quantum information theory. And if you had such decoders, you could do so. Okay. Right, so that's the statement here. So the reason I think that, we have a conjecture that this is true. I mean, naturally, you'd expect us to have a conjecture, right? So we expect it's true because sort of intuitively, for the 2-sender case, we have a measurement that works for distinguishing these states, right? So in some asymptotic limit, we can think that these states, since they're distinguishable, they're approximately orthogonal. Okay, so when we go to 3 senders, why wouldn't it be the case that as long as there aren't too many messages, why would these states not be distinguishable or orthogonal? Okay, so there has to be some way to distinguish them. We just need to find it. So finally, these are some of the offspring of this work. There's a poster by Shen-Chen Zhu on this idea in the entanglement-assisted case. There's some recent work with Ivan Savov on broadcast channels and relay channels. And yeah, so there's likely other scenarios where we can make use of these tricks, and it'd maybe be interesting to do so. Okay, thank you very much.
So I see a hand there by Beth.
Yeah, I have, well, the main question I have is in this sequential decoding method, you have hidden, compared it to the square root result, but hidden in the square root result is the idea that in the Pareto bound, that Pareto, Schumacher, Westmoreland, that you could do better in some situations with entangled measurements, even though you're using product inputs. But now with your sequential method, you're going through a code work book which consists of products. So where is the entanglement coming in the end measurements, and if not, how come you get the same result?
So it is there. These typical projectors are collective measurements on all of the channel outputs. Okay? So
I guess
the sequential decoder is constructed from these typical projectors. And so each question in the sequential decoder is what you call an entangled measurement.
Okay, but then I don't understand how you described it as essentially going through the code book you started with.
Okay, that's a good question. The code words are tensor product states, but the typical projectors are collective measurements. So corresponding to each code word, there's a typical projector. And that's the question that we're asking as we go along. So, you see? I don't see any hands.
You mentioned the advantage for optical channels in the low photon regime.
Right.
The conductor regime. Can you say something about that?
Right.
Question for the people in the back. I'm not sure if they can hear talking in front.
The question was to say something more about optical channels in the low photon number regime. Okay, so the answer to that is a classical strategy would be to use homodyne detection at each channel output for an optical channel. Okay, so this effectively induces a classical channel. You could also use heterodyne detection at each channel output. And since they induce classical channels, they'll have particular capacities. Okay, homodyne will be larger than heterodyne in the low photon number regime because the vacuum noise is relevant, and the homodyne detection does better against the vacuum noise. But this collective HSW measurement can beat both of those. That ends up being the actual capacity. I forget the exact numbers, but homodyne is better than heterodyne for low photon number, but collective still beats both. Heterodyne is larger than homodyne in the large photon number regime, and heterodyne asymptotically approaches HSW. There's another question.
Is there any intuition for whether this could become an n-party sender protocol?
Right. So the question was, is there any intuition if this could be applied to an n-party sender? I gave you the intuition in terms of, I think these states are approximately orthogonal because they're distinguishable in the two-sender case, so I thought, why wouldn't they be distinguishable in the n-party case? There is more, well, yeah, I'm not sure how far it goes beyond that. It's the fact that we're able to come up with something for two senders. We think that it could work for three senders, but you'd need far more advanced techniques than what we're using here to do so. So this is a very good open question.
Okay, if we don't see any further question right here, we'll continue the discussion over coffee break, and let's thank the speaker again.